Alright, so for those of you that weren't here the day we learned about taking the area under a curve, I'm going to just give you kind of a new note sheet so that you can not fall behind and know what you're doing. The process of finding the area under a curve is called integration. And we can find this area by filling the region with rectangles that we know the area of. Now, by this I mean it's kind of like an M&M jar. So like if you know how big an M&M is and they put a bunch in a jar, you kind of can guess, around how many would be in that jar. So that's kind of what you're going to do. You're going to fill this space with rectangles, and you know the area of the rectangles, so you can kind of find the area underneath this curve. We're going to first draw a curve. So it's going to look something like this, and it's going to go from A to B, and we're going to block off this area that we want to find. So all under here is what we want to find. Yeah, hold on. Okay, so we want to find the area under this curve, and we're going to break it up into two triangles to start. So split it in half and make these into, oh, I keep saying triangles, rectangles. And if you think about it, this is close. Okay, this is really close to finding the area if we can find the area of these two rectangles. But we have this little part up here and this little part up here which are extra, and that's not very good. So this is close. But we have something that can make it even better. So if we change this curve, it's going to be the same curve, but we're going to change the rectangles so that they're smaller. So look, draw another curve like this, and I'll go from A to B. We're going to black it off like the last time. And like always, we want to find this area underneath this curve. So that's good. But instead of making only two rectangles inside of here, we're going to make a bunch. So we want to make them all the same width. And I'm going to try to do that, but sometimes they don't look perfect. Okay, so that's pretty good. And now we're going to make these into rectangles, so we got to complete them. So they go like this, like this, like this. They end up getting super, super small and almost like a rectangle. So if you look at this, all these little extra areas that we get are so small that they don't even really matter. So this is more accurate. And that's good. So if we were to actually find the area for every single rectangle and add them all together, we would take the width of each of these, which is delta x, and then we would find the height of each of these, which is f of x. So the y value, and that would be the height. So if we were to write an equation for this, area under the curve for this picture is going to be the area equals the area of the first rectangle, so f of x1 times delta x, that's the length times width for the first guy, and then we add it to all the other areas, so it'll be f of x2 times delta x plus f of x3 and so on, and you end up getting plus dot 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 plus, and however many rectangles you have, it could be f of xi, where you pick I, delta x, okay? And instead of writing this all out, it's a lot easier to just write it in a summation. And don't get weirded out by the notation, because it just means adding, okay? So this is equal to the sum, which that means the sum is called sigma, and it's going to be from I equals to 1 all the way to n. So you pick I, it's going to be 1, 2, 3, 4, all the way to n, and of the function that we're going to add, so xi delta x. Okay, so that is the area under the curve. But now here's the deal. Each rectangle right now, we can see the width for each of these. And right now we only fit 1, 2, 3, 4, 5, 6 rectangles in that space. To get a really, 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 really accurate integral or area, we want to make those rectangles as small as possible in the width department, okay? So the way that we do that is we say that n is going to go to infinity. We're going to make n rectangles fit inside that space. And the way that we do that is take a limit. So we're going to take the limit of a sum, and that's actually what a definite integral is. So this means integral going from a to b of f of x dx. So that just means with respect to x. But we're not going to focus on that right now. That's going to be tomorrow. Today we're going to focus on taking the limit of the sum, which essentially is the same thing. So we're going to take the limit as n goes to infinity of the sum of I equals 1 to n for f of xi delta x. Okay? And that's going to be the equation that we work with today. Now, you might ask yourself, what is xi? What is delta x? Well, for any given curve, we can find that delta x is just that change in a and b times how many times that happens. So how many rectangles. So delta x is b minus a over n. So how many rectangles? Xi is actually going to be what you pick as the number. So xi is going to be a, so the number that you start with, which in our case is mostly 0, but a, plus I delta x. Okay, so however many delta x's you pick. Alright? Now, what is I? Well, I is that number, like I said, that you pick, and it's going to be added together, so it's a sum. So if you think about it, I to the 1 is equal to 1 plus 2 plus 3 plus 4, and so on, and they come up with this equation that pretty much represents summing something to the 1 to n, okay? I to the 2 is 1 to the 2, 2 to the 2, 3 to the 2, and so on, alright? And this isn't like I, the imaginary I. This is just picking a number. So you could almost say like x squared, right? It'd be like you pick x. So this is I cubed, I to the 4, I to the 5th. Now this is going to come in handy when you do these integrals, because instead of adding all these numbers up and coming up with this equation, I'm just going to give these to you. So you're going to plug in, if you ever get I squared, you're going to plug in this equation. Okay, if you ever get I squared. If you ever get I cubed, you're going to plug in that equation. So you just got to be aware of what I you have. Okay? Alright, so now we're going to go on to actually finding the area of a region of a graph. So on the back here it says use limits to find the area of a region between the graph of y equals x squared and the x-axis from 0 to 1. So I'm going to draw a little picture, and I'm going to use some extra paper because I want you to be able to see it. And we're going to draw a picture of this. This is actually a graph from 0 to 1 of y equals x squared. So it'll look something like this. It's like a half of a parabola, or part of it. And we want to find the area from 0 to 1 underneath this curve, so all of this. Right? So how do we find all of that? Well, we're going to take the limit of the sum, okay, of all the rectangles that we could fit in there, as many as possible. So let's start out by writing out our integral formula. So it'll be the integral from 0 to 1, okay, of x squared, because this is y equals x squared. So that's our function, dx. Now this is just notation, so we're going to say the limit as n goes to infinity of the sum from 1 to n of xi squared, because it's x squared, delta x. Okay, and that's your starting point. Now what you're going to do is actually find delta x, and you're going to find xi. So let's go look at our formulas that we have in the front and figure that out. So delta x is actually equal to b minus a over n. So we're going to do that. b is 1 and a is 0, because you're starting from 0 and going to 1. So it'll be 1 minus 0 over n. 1 over n. Okay, that's delta x. Now we got to find xi. So xi is equal to a plus I delta x. We're just going to plug in what we know. So a is 0 plus I, and delta x is 1 over n. So we get I over n. Okay? Now those things are what we're going to plug into our formula. And I'm just going to write across so I don't have to write the limit so many times. But you do have to make sure you include the limit in the sum, because that's part of the problem. So we're going to say the limit as n goes to infinity of the sum from 1 to n of xi squared. So we're going to do I over n squared, okay, times delta x, which is 1 over n. And that's actually equal to, we're going to square the I, square the n, and then multiply. So we end up with I squared over n cubed. Okay, that's where we're taking the limit of the sum. Now the sum part is really this I squared, because you're really summing like 1, 2, 3, 4, but you're squaring each term. So what we can do to drop this sum notation is we can actually fill that in with the formula from the front of the page. So this is a formula that represents a sum. So really this is the limit as n goes to infinity of, when it's like 1 over n cubed times, and it's like 1 squared plus 2 squared plus 3 squared, and so on. Okay, and instead of writing that, we're going to just say it's 1 over n cubed times the formula on the front, which is just n, let's see, n squared. So it's just n times n plus 1 times 2n plus 1 all over 6. Okay, and that's just from the front of the sheet. Now this is just algebra, so we're going to take the limit of whatever this is. So I'm going to cross out an n and make that n squared, okay? And I'm literally going to just FOIL these and combine n's and see what I get. So the limit as n goes to infinity of 2n squared, so first side inside last, plus 3n plus 1 all over 6n squared. I'm going to take out a 1/6 just because that might be a little bit easier. So it's equal to the limit as n goes to infinity of 1/6 outside of, and then I'm going to put each of these terms over n squared. So we're going to do 2n squared over n squared plus 3n over n squared plus 1 over n squared. Now here's the cool thing. You can start canceling these n's, so those go away. One of those goes away. And now we can take the limit. Remember, when we take a limit, we're technically plugging in. So we're plugging in infinity for n. So we're going to say limit as n goes to infinity of 1/6 times 2 plus 3 over n plus 1 over n squared. We're going to take the limit of each of these numbers individually. So you're going to take the limit of 1/6, the limit of 2, the limit of this, and we're going to add them all together. So the limit of 1/6 is just 1/6. The limit of 2 is just 2. Okay, there's nothing to plug in there. But as we plug in infinity for 3 over n, it becomes 3 over a huge number, which if you plug it in your calculator, it's going to be super close to 0, and we're taking a limit, so it's going to head to 0. So the limit of 3 over n is really just 0. And then the limit of 1 over n squared is also 0. So your area under the curve is 2 over 6, or 1/3 units squared. Okay? So that is the notes. And if you have any questions, we're going to continue this later on. All right, have a good day.